Okay. Thank you so much for the kind introduction. It's my great honor to be here to introduce our recent study on discovering security issues in blockchain ecosystem. So people, including us, are optimistic about the development of FinTech blockchain. Its market size is projected to reach 22 trillion in 2034. However, the underlying blockchain platforms and smart contracts may not be as secure and robust as what people may expect. It has been shown that the attacks on the blockchain ecosystem has caused more than 35 billion finance loss. So this figure shows the major components in the blockchain ecosystem. We can see that all the major components, including the front end, the network, the layer 1, layer 2, or even layer n infrastructures, as well as the smart contracts, as well as the third-party service, may be vulnerable to different types of attacks. So my research aims to developing a holistic approach to safeguarding blockchain ecosystem from two aspects. One is to identify vulnerabilities in all those systems and softwares. In particular, we try to identify zero-day vulnerabilities that have not been known by anyone else. And then we will develop novel algorithms and tools to facilitate the ultimate security assessment. We also develop tools to help developers detect and fix bugs. So another perspective is to defend against different types of attacks. We will try to investigate the stealthy malware and try to detect the attacks and trace the attackers. We also develop new systems to protect the victims from the attacks. So in today's talk, we will focus on the vulnerability discovery part. So actually, we have been investigating the security issues of blockchain infrastructures. For example, we have identified security problems in major blockchain platforms like Ethereum and its variant. We recently identified some inconsistent bugs in its gas mechanism. And we also discovered a set of DOS vulnerabilities that will affect the liveness and other features of the blockchain platform in blockchains using MPT. And we also identified some DOS weakness in the blockchain resource model. And last year, we also identified several severe vulnerabilities in popular roll-up systems, including Arbitrum, Optimism, and Polygon. And we also uncovered some exploitable vulnerabilities in the Ethereum smart contract verification service. So besides the blockchain infrastructures, we have also been investigating the security issues in smart contracts running on top of different types of platforms, including the Ethereum virtual machine, WebAssembly, Algorand, Move, as well as other programs like Circum programs and even Bitcoin scripts. For example, last year, we developed the first GPU-assisted fuzzer for smart contract, Ethereum smart contract. Our system can detect many more vulnerabilities than SOTA with more than 10 times the throughput. Then I believe you may be wondering why the blockchain or normal software have so many bugs. Our experience reveals several causes. One is that the system is very complex, including the blockchain system. They are very complex with millions of lines of code, as well as many interacting components and third-party libraries. Another major reason is due to developer error. For example, the developer may misunderstand the requirements and the standards, for example, those EIPs. And moreover, some designs may not be carefully investigated so that it will lead to security issues in the implementation. So both the complexity and the developer errors will lead to inconsistency in the blockchain systems. And the inconsistencies will cause security consequence. And at the same time, nowadays, the software testing is usually inadequate because the existing test cases may not be able to cover all parts of the programs that are under testing. And sometimes the test case may not actually represent the real user behavior or edge case. So in today's talk, I will introduce several inconsistency-induced bugs in the blockchain infrastructures, which have been discovered by our recent studies. One type of inconsistent bugs were found in blockchain transaction fee mechanism, and another type of inconsistency-induced bugs were found in ZK rollup. So the transaction fee mechanism was designed to prevent resource abusing. Basically, you will charge users based on the resource usage. In Ethereum is the gas mechanism. Basically, the gas mechanism requires user to pay for computational effort for each operation executed on the blockchain. Interesting, we identified several types of TFM inconsistent bugs. That is remarked by the discrepancy between the fees users are charged and the actual computational resource utilized. In particular, we identified two types of inconsistency-induced bugs. One is called the resource inconsistency bug, or RIB. So basically, the blockchain allows for varying resource utilization at the same gas fee. For example, if we send the Ether in a transaction, but both the sender and the receiver are the same. In this case, no Ether transfer occurs, and the balance remains unchanged. However, the user will still be charged the gas fee for the disk write operation involved in updating the Ether records. Another type of inconsistent bug is called a fee inconsistent bug, or FIB. So basically, the users may incur varying fees for the same on-chain resource usage. For example, when we send the internal transactions, that is the transaction sent by one contract account to another contract account, if the recipient does not exist, the sender should pay the gas fee for creating a new account in the disk. However, if we use the external transaction, that is to send the transaction from an EOA account to another contract account, if the recipient does not exist, the sender does not need to pay the gas fee, although the new account will be created in disk. So we developed a new fuzzing tool called AusPax to identify these two types of inconsistent bugs. So I will skip the detail of our system, which can be found in our paper. Here I would like to introduce some of the bugs discovered by our tool. So we uncover 13 unknown TFM inconsistent bugs, which have been confirmed by the Ethereum core development team. And I will introduce some financial loss that can be caused by the bugs. For example, the first bug occurred when a transaction calls a pre-combined contract with zero-length input data. So usually, if a user invokes a pre-combined contract with zero-length input data, it means there is something wrong with this transaction. And if the user says only 21,000 gas, then this transaction will be reversed, resulting in the loss of this 21,000 gas. But if the user would like to set a high transaction fee, the user will incur a further gas. That is used to call the pre-combined contract. Another bug lies in the fact that a disk write operation is not executed, but a gas fee is still charged. The third bug is triggered because the revert transaction does not update the state of the blockchain in the disk, but is still charged for the gas fee of disk writing. So nowadays, when a transaction updates the state, the changes are initially stored in memory due to the cache mechanism introduced by the Ethereum. And they will not be immediately returned to disk. And the updates are only returned to disk once all the transactions in the block have been executed. However, if the transaction is reversed, the update state will be reset in memory and not returned to disk. So in this case, both the normal transaction and the revert transaction will incur the same gas fee for state updates. But only the normal transaction will write the updates to the disk. There are some other types of the bugs so for example, this bug occurred because the memory write during account modification are incorrectly charged as disk write. And another one arises because the Ethereum optimized its storage structure to reduce disk risk, but it didn't adjust the corresponding gas fee. Then we investigate the financial loss that may be caused by the bugs. We measure the financial loss on Ethereum and BSC using 1.5 million blocks. And we found that on Ethereum, the bugs affect almost all the blocks and cause 981 million USD fee loss. Basically, we can save the money and use it to do other useful things, right? And on BSC, the bugs also affect almost all the blocks and cost around 9 million USD fee loss. So besides the financial loss, the bugs can also be exploited to launch attacks on the blockchain platform. For example, the bug 2 occurs because the gas fee for writing input data to disk is lower than that for writing bytecode. And another bug arises because the internal transaction should pay the gas fee to write a new count on the disk. And we also demonstrate how to exploit these 2 new bugs to launch a new denial of service attack. Basically, the idea is to flood the network with external transactions with input data of maximum length to the blockchain. And so I will skip the detail, but I will show the results. The experimental results show that our new DOS attacks can significantly increase the block size. Actually, it amplifies the block size 96 times and increase the wait time of transaction around 5 times. Okay, so for the first work, we identified several inconsistent induced bugs in the gas mechanism. We have been also investigating different aspects of the gas mechanism. For example, we analyzed and optimized the overcharge issue on blockchain storage with a paper published in this year FAST. So this work has contributed to a new EIP, EIP 7863, the block level warming. And last year, we introduced our work that is a new type of DOS attack with persistent effect on blockchain by manipulating MPT. So in the second part, I will introduce some inconsistency-induced bugs in ZK rollups. So ZK rollup aims to address the scalability issue of layer 1 blockchains. Basically, the transactions will be executed on the layer 2 blockchains. And for each batch of the transactions, ZK proof will be generated. And this figure shows the major components as well as the interactions of those components in Polygon ZK rollup. For example, it has a transaction pool. The user transactions will be initially placed in the transaction pool, which will be pre-executed. And the transactions having execution errors will be discarded. The sequencer will prioritize the transactions from the transaction pool, assemble them into batch, and submit them to layer 1. It will also send the batch to executor for processing. The executor will use a virtual machine to execute the transactions, measuring the execution in steps to limit the resource usage during ZK proof generation. So the transaction finalization process of the Polygon ZK rollup consists of 2 stages. The first stage is called the faster transaction finalization process. Basically, you will execute the transactions and groups the transaction into batches and send them to the layer 1 Ethereum. The second stage is called the hard transaction finalization process. Basically, you will generate and publish the ZK proof for the L2 transactions. And we identify 2 types of finalization failure bugs. Some are caused by the inconsistency. One is called the faster finalization failure bugs. That occurred when the layer 2 components either terminate unexpectedly or become stuck. And another type of finalization bug is called hard finalization failure bugs. They occurred when the layer 2 components involved in this hard finalization process either terminate unexpectedly or get stuck. And we also developed a fuzzer to identify this type of issues. And here I will just introduce some of the bugs caused by the inconsistency. So the first one is due to the inconsistent behavior among components. Basically, the finalization process involves multiple components. And the inconsistency in checking and processing can lead to the unexpected issues. For example, the maximum execution steps allowed by the executor are smaller than that required by the sequencer. In this case, when the sequencer forwards a batch whose execution steps exceed executor's maximum limit, the executor will trigger an out-of-counter errors. Once triggered, the bugs cause the sequencer to stop producing subsequent batches and L2 blocks. So another inconsistent issue lies in the discrepancy between the pre-execution and the batch assembly environment. Basically, the pre-execution check will discard transactions triggering this error. However, such transactions may still pass the checks. The attacker can also hide these errors in the smart contracts. So if you are interested in it, you can take a look at our paper. In this case, if the error is triggered, the sequencer still consider the corresponding transactions valid, and you will reserve them in the transaction pool. So the takeaway is that we conduct the first security analysis of the popular ZK rollup solutions, and we discover many vulnerabilities. And we have also investigated the security of other OP rollups, and we identified several double spending vulnerabilities in Arbitrum and other popular OP rollups. So in summary, the blockchain ecosystem may contain many hidden vulnerabilities. Therefore, a thorough investigation of all the components and their interactions are required. The second one is that more security-aware developers and experienced security researchers are needed to secure the blockchain ecosystem. At PolyU, we provide Asia's first MSc program in blockchain technology. That's all my talk. Thank you so much.